Hi everyone. In Unit 2, we're going to look at two types of isomers, constitutional isomers and stereoisomers. And as an introduction to these two types of isomers, we are going to define and give an example of how to draw constitutional isomers, and then we'll have an intro to chirality, which is a property displayed by stereoisomers. This is probably new to most of you. I don't normally wear a headset. That's going to come into play also in this discussion, or one of our first discussions about isomers. Okay, and let me find my document camera. Oops. Okay. Why don't we start out with isomers, and then we'll look specifically at constitutional isomers. So if you have two molecules, let's say molecules A and B, and they have the same molecular formula, they could be, the relationship between those two molecules can be a couple things. Now, sorry about this. They could be identical to each other. So if they have the same molecular formula, these two molecules, A and B, they could be identical. Or they could be constitutional isomers. The other option is that they could be stereoisomers. Now, identical means that, well, you can overlay one molecule on top of the other, and remember, it doesn't have to be, you don't have to keep the molecule static, so don't worry too much about what this molecule is. But this molecule here that I'm showing on the screen would be considered the same identical molecule even if I had drawn it with this methyl group going downward, because you're allowed to twist the molecule to try to figure out whether those two are identical or not. So just like my hand is still my hand whether I draw it like this or if I draw it like this, thumbs up, thumbs aside, or if I give the victory sign, it's still my hand. It doesn't change the identity. Okay. Constitutional isomers, they differ in their connectivity. Differ in connectivity. Actually, let me go back to identical. One example that I might have done previously is we all know that that's butane. Okay, but if a classmate draws this molecule, they look different on paper, but they're both butane. So we will say both of these are, well, these two, the relationship is they are identical. Okay. Differ in connectivity. So how do the atoms, the order in how the atoms are connected? So let's take butane again. Okay. 4 carbons connected in a row. But if I have 4 carbons and 3 are connected in a row, and 1 carbon is part of a branch, those definitely have the same molecular formula, but now these are not the same, they're not identical, these are constitutional isomers. Stereoisomers, we'll get to later. Stereoisomers is a concept that is a little bit abstract. We're going to be using in this video several models, so we'll set that aside. All right, constitutional isomers. So, for instance, if you have these molecules, let's do 5 carbons. Actually, let's do do a different type of molecule that we haven't really talked much about. Let's talk about an alcohol. So that is an OH group, or a hydroxyl group, which makes the molecule an alcohol. My formula is C12345H 1, 2, 3, 4, 5, 6. No hydrogen there. 7, 8, 9, 10, 11, 12. Let's count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, okay. If I wanted to draw a constitutional isomer with this, I would just rearrange the connections of the atoms. Maybe I could do... how about this? And then put an oxygen here. Okay. 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. 1 oxygen. I wanted to do this example because we haven't seen many examples where we didn't have either carbon or hydrogen. So here we have an oxygen. You notice with line drawings, you draw the hydrogen, you explicitly draw the letter H for any atom that's not a carbon. So the shorthand for line drawings or line angle drawings is that you could remove the H's, you don't have to draw them explicitly for any hydrogens that are connected to carbon. But if we had a nitrogen that had a hydrogen, or an oxygen in this case, you have to put the you have to draw out the hydrogen. So these two are constitutional isomers. So if we had something like this, though, okay, those are 5 carbons. 1, 2, 3, 4, 5. 1 oxygen, great. But how many hydrogens do we have? Okay, test yourself. Okay, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're too short. So what would I call these two? Okay, they're not isomers, so they're not identical, right? So I mean, they're totally different. And in a multiple choice problem, most likely you would say these are none of the above. They're not identical, they're not constitutional isomers, and they're also not stereoisomers, right? Because they have to have the same molecular formula. So we'll say none of the above. They're not I, Ci, or even Si. Okay. Well, I'm ready to talk about stereoisomers. You'll have more practice probably in some of the last videos of Unit 2, but really Unit 2 is us getting a grasp of what stereoisomers are and how to name them, because these are fairly easy. You know how to name alkanes, 2 different constitutional isomers of hydrocarbons. But what about stereoisomers? Okay, it's gonna seem like we're gonna take a little bit of detour, but what I want to talk about are my hands. Why? Because objects and molecules and we could say some objects and some molecules have a property that I will call handedness. Okay. Has the property of my hands. Well, what is so special about my hands that we have a set of molecules that are based or that have a property of my hands? Okay. So here's my left hand. Okay. Here's my right hand. My question to you right now is, are they identical? Okay. Hopefully you can tell that they're not identical. Okay. Because if you play baseball or softball, if you're right-handed, you usually wear your mitt on your left hand. And if you take the left-handed mitt, that won't fit your right hand. So that tells me that my 2 hands are not identical. So that's one statement that we hopefully know is true. My left hand is not identical to my right hand. Okay. So if we take a look at our A and B molecules, my right hand and left hand are not identical. So maybe they're constitutional isomers, or maybe they are stereoisomers. Okay. So you could even treat objects as having these types of relationships, not just organic molecules. Okay. How do I know they're not identical? Besides, that idea that I could wear a left-handed mitt on just my left hand and not my right hand. There's a term called superimposable, but my hands are non-superimposable. They can't be overlaid on each other and have everything match. So I put my hands on top like this, my thumbs don't match. But you might ask, well, isn't this superimposable, right? My palms going together. See, all my fingers match. My thumbs are with my thumbs, my pinkies with my pinky. But the thing is, this is not superimposable because the palms are facing the wrong way. Superimposable is this, like these two objects. You could overlay one on top of the other, and everything matches. Okay, everything matches. Okay, everything lines up. Not the case for my hands. My hands are non-superimposable. But what else do you realize about my two hands? Well, what happens when I put them palm to palm? Okay, they may not be identical, but they are mirror images of each other. So that's interesting. Okay, not, two objects that have the same molecular formula aren't necessarily mirror images. Look over here. These are not mirror images, right? If I put a little compact mirror right here, I don't have a mirror with me, but if I put a mirror right here, will I see in the mirror this molecule here? No, you wouldn't. But if I have my hand here and I put a mirror right here, what do you think I'll see in the mirror? Honestly, you would see my right hand. You would see the image of my right hand. So these are, not only are they non-superimposable, we have a statement called non-superimposable mirror images. My left hand has a non-superimposable mirror image. My right hand has a non-superimposable mirror image. So we're talking about now individual atoms or individual molecules. So the statement that I believe is true is my left hand has a non-superimposable mirror image. Now you might ask yourself, well, aren't all mirror images superimposable? No. Let's go back to the caps. Here I have a cap, pen cap. Do you see that this other pen cap on the right is the mirror image of this pen cap on the left? So these are mirror images, but they are mirror images that are superimposable. So these two are identical. Remember, superimposable means identical. Non-superimposable, not identical. So these are superimposable mirror images, and they're identical. My hands are non-superimposable mirror images of each other, and they are, well, that means non-identical. That means not identical. So these two are equivalent. Not identical and non-superimposable. Same. Just a fancy way of saying identical. So here comes a new word, So we have handedness. If your molecule has a property like my left hand or right hand, where the mirror image is non-superimposable, you could say that that molecule has handedness, or you could say it is chiral. And you use the term chiral to describe one object. So my left hand is chiral because it has a non-superimposable mirror image. My right hand is chiral also. So what about my pen cap? My pen cap is not chiral because the mirror image of it is superimposable. They are identical. That means it is achiral. Okay. All right, I'm going to write that on the next sheet of paper. And we're going to now look at some examples also. So again, when you use the word chiral and achiral, you're talking about an object or one molecule. When you talk about them being non-superimposable mirror images, you're talking about two objects and their relationship, like my left hand and right hand. So I'm just going to choose my left hand. My left hand is chiral, but my pen cap is achiral. That's interesting. Okay, now so that is a typical problem. They show you, your professor shows you a molecule, and you have to say, is that molecule chiral or achiral? Does it have the property of handedness? Okay, and like my right hand and my left hand, they both have a property of handedness because their mirror image is not superimposable, whereas the mirror image of these two things, whoops, like that, are superimposable. Okay. Okay. So we have the term handedness, but really we could call it chiral or achiral. In terms of like an adjective, or sorry, a noun. See, this is an adjective. It is chiral. Handedness can also be called chirality. You have the property of chirality if you are chiral, you the molecule. Okay. I know there's a lot of terms like why do we have to have another term for identical? Okay. It's just because when you do this with models, you're literally trying to impose molecule B over A and see if everything lines up. Okay. So here's an example. We're going to go back to our molecule that has an OH, and I want us to make these two molecules. Okay, that. And now we're going to make the OH away from us. So pause the video. I'll make the models as well, and then when you're done making the models of these two, unpause the video. Okay. So I've made the models ready, and we have this molecule on the let me do the one on the left first. Yikes. So here's the molecule on the left. Do you see how the OH is coming towards us? And we have the zigzag pattern, the same as on the paper. You got to match the zigzag pattern to demonstrate this properly. And then also I'm going to push this hydrogen a little away. Okay. How about this molecule on the right? That molecule on the right is this one. Okay. And the OH is going away from us. Those two molecules have the same molecular formula, so I got to decide whether they are identical, constitutional, or stereoisomers. Look how I'm going to decide first whether they are constitutional isomers. Okay. I got to check if they have the same or different connectivity. If they have the same connectivity, they are either identical or stereo. If they differ, you're automatically constitutional. You have to be constitutional if they differ in connectivity and they have the same molecular formula. you're going to verbalize CH3, CH3, connected to CH, connected to CH, connected to OH, connected to OH. I don't care if it's wedge or dash. I'm just looking at the connections. So back to the CH, connected to CH2, connected to CH2, connected to CH3, connected to CH3. These two have the same connectivity. So they are either identical or stereoisomers. Okay. Identical or stereoisomers. Sorry, I keep touching the microphone. I don't know if it's picking it up. Alright. How do I check now if they are identical? Okay. First, when you start to learn this, you should make models. So here's the model on the left. Okay. OH towards us. Here's the model on the right. OH away from us. Same zigzag though. Okay. When I superimpose the zigzaggy carbons, do you see how everything matches? Okay, they align each other. But look at the OHs. The OHs are going in the opposite direction, like one towards us and one away from us on the picture. And in the model, they're also going in opposite directions. So right now, they are not superimposable. Well, what if I turn it over? Okay, turn one of the molecules over. Well, if I turn one of the molecules over, okay, look what I can match. I can match the OHs. See how the OHs and the carbon match? And even some of these other carbons match. But what do you notice? I'm going to lift this up a little bit further up. Do you see how going to the left of this carbon here in the middle, we have two carbons, and like you could call it an ethyl group. The ethyl group on this carbon is to the right. So the OHs match, but now the methyl and the ethyl groups don't match. The methyl and ethyl groups don't match. Okay, so by models, these are not identical. So by models, we should say that they are stereoisomers. But let me show you also now, what if you don't have models? How do I do this? This is a good skill to have because you need to be able to quickly surmise how to rotate and flip molecules or turn over molecules to try to make them look the same. Because if I take this molecule right now and take it off the paper and put it right here, yeah, the carbons match, but not the OHs. So why don't I try something else? Why don't I turn this over? If I turn over this molecule here, do you see what I draw? This is a skill again that you want to develop. I take that molecule on the right and I turn it over. Huh. If I turn it over, I get the OH towards us, but look what doesn't match now. The wedge OHs match, but see the carbons don't match, right? The ethyl group is on the left, the methyl's on the right. So these are A and B are stereoisomers. Not only are they stereoisomers, take a look at these two. Right, this is A, and I redrew B when I flipped it over. But this is still B. This is still B, so don't get that confused. These look different on paper, but I used the same molecule to draw these. I just turned over one of them, turned over the molecule to make it look like this. So let me just make sure this is right. Oh, that's why it didn't look right. The OH is on the wrong carbon. Oh, yikes. Sorry about that. Not only that, but the zigzag was incorrect. So that got me a little bit worried. Oh, and I'm going to put the H here. It doesn't matter where you put the H, but you'll see why in just a minute. Why I put the H there. Okay. Now if I draw this molecule, so this is A. If I draw molecule B, I have this. Oh. What did I just prove on paper now. Okay, again, sorry about that whiteout. Let me see if I could do. Yeah. Okay. Man, that got totally messed up. 4 carbons. 1, 2, 3, 4. What I want to prove to you is that when I turn over B to make it look like this and put it next to A, oh, these are mirror images. These are non-superimposable mirror images. They are like my hands. If they are like my hands, this molecule is chiral. This molecule is chiral. Okay. And there's a special term. So I know it's very term heavy, but if you have A and B, again, here's the flow chart. You could be identical. You could be constitutional isomers, but so far we've shown that they're not constitutional isomers. We've shown that they're not identical, right? So they have to be stereoisomers. But there are 2 types of stereoisomers. Okay, this is the last categorizing for isomers. You have something called enantiomers, and you have diastereomers. Okay. Enantiomers are like my hands. They are stereoisomers that are mirror images. Okay, so these 2 are enantiomers. Diastereomers are stereoisomers that are not mirror images. And we have not seen an example in this video of this just yet. But what I want to impress upon you is that enantiomers are my hands. My hands are enantiomers. That is a very important concept in especially biology. Okay. So I mentioned my headset. So how do I? Oh, do I have to? Hopefully you can still hear me. How's my headset? Is my headset chiral or achiral? One way to check is to draw the mirror image and see if they are superimposable. But see this little piece here, it's on the left ear piece. So if I draw the mirror image of this microphone will be on the right ear piece, and they would not be superimposable. Okay? So in terms of terminology, this object is chiral because it is not superimposable on its mirror image. There are a ton of molecules that are chiral, but there's also molecules that are achiral. Okay, let me draw you a molecule, and you have to decide whether it's chiral or achiral. So you'll do this at home, because I'm going to do the same concept. I'm going to take a carbon chain and I'm going to put OH wedge and OH dash. Remember, we have now decided these are enantiomers. And these 2 are identical because all I did was flip this or turn this one over. But I want us to ponder what happens if I remove 1 carbon and I have this. Make models, because I want to know the relationship, and for you to prove to yourselves, if you don't have a lot of experience rotating molecules in your mind, make models and tell me if they are identical, constitutional isomers, enantiomers, or diastereomers. Okay. We'll pick this up in the next video. Okay.